Hello, everybody, and welcome back. We're going to continue doing these really interesting problems from mathleague.org. We started doing this yesterday. This is from their state championship, and on this particular set of questions, we saw that there were quite a few creative things. There were some neat questions with neat numbers, surprising ways to use geometry, and we even got some questions about the Cherry Blossom Festival in Japan. What will there be today? I don't know. Actually, if you haven't been here before, I will warn you that what you're about to see is something that no one's seen before, including me, in the sense that, well, actually, that's not quite true. There are students who are watching this who have done these problems before. But what I'm doing is I'm trying to do the questions without ever having looked at them before. And the reason is because I want to show how somebody could think through how to solve a question if it's the first time you ever look at it. I see that Math Magic says, well, maybe I have seen this. Maybe there are some people who are watching this who have seen these questions before. So good, then you'll have a review. But I won't. So let's continue and go on. What's the next question? Let's see. State sprint number 19. A positive whole number n satisfies the property that no number with at most 5 divisors has a sum of digits of n. What is the least possible value of n? Whoa, okay, so there's a lot of words in this sentence. There are some things about least possible value, and I've got something of sum of digits being n. And there's this like no number with at most 5 divisors. I see. So the reason it's asking what's the least possible value of n is if I told you, hey, I have an n, it's called a billion. Well, of course there's no number with at most 5 divisors. Well, actually that's not true. That might be. Oh, I don't know that's the case. Okay. Let's keep thinking this through. So I need to say, what are the numbers that could be the sums of the digits of numbers with at most 5 divisors? Okay. Well, if I have at most 5 divisors, okay, so I need to find some kind of a number. Well, I guess I have to look at numbers or possible digit sums of numbers which have a lot of divisors. So I'm thinking about this. These questions are interesting. Because the reason I'm pausing is I'm saying, like, actually, you know, I can make a number which has only 2 divisors by choosing a prime number. And then suddenly this is something telling me that there's, you know, it's just like if I told you a number n like a billion, I was trying a billion. I was like, but am I sure that there's no prime number whose digits add up to a billion? That could happen. Well, one thing I do see here is that if I want to have a number with at most 5 divisors, sum of digits makes me think of 9. So I'm going to start to play around with this. Yeah, and there are infinitely many prime numbers. That's why I'm scared. So what I was saying is, like, at first I was just thinking, oh, make n big enough, you'll be fine. But that's not completely clear, because if I just chose some really huge prime numbers, maybe I could make prime number whose digit sum adds up to a billion. So instead I'm starting to play around with, like, 9, okay? I'm like, the sum of the digits. If the sum of the digits is a multiple of 9, then I know that the number itself is a multiple of 9. Does that help? So now I'm thinking about, yeah, I'm just trying to even find one value of n that I can prove something, okay? And the easiest way to make sure I don't have to worry about prime numbers is if I'm just like, well, what if n is a multiple of 9? Like, what if n is 9 itself? If n is a multiple of 9, well, in that case, what I would get is that the number, wait, yes. I'm saying, like, sorry, n is the wrong number. I don't want to call it n. Let's call the number m. Okay, and I'm talking about m, and you can see I'm just thinking about this. Okay, so number with at most 5 divisors, that's going to be my m. Okay, m is going to be this number with at most 5 divisors. If m is a multiple of 9, wait, is that what I want? No, I actually did want n. I did want n. If n is a multiple of 9, but I do have this m here, which is useful, then m is also a multiple of 9. Oh, I see what's happening. So then m is also a multiple of 9. And now what do you know about the divisors of m? I know that the divisors of m, they definitely include 1. And also like all the things that make a 9. 1 and 3 and 9. And there will also be an m somewhere. Okay. Now this is kind of interesting. Because I'm like, I just want to make it so that I want to force there to be a lot of divisors. That's sort of what I want to do here. I want to force there to be 6 or more. Why are we doing multiple of 9? We're doing multiple of 9 because I'm trying to figure out how to get even one value of n that I can prove something about. The reason is because at first I was like, hey, just use n equals a billion. Surely there's no way to have a number with at most 5 divisors whose sum of digits is a billion, right? Let me just write down what I was hoping at the beginning, and I found out it was hard. Here is something which is like not obvious. I don't even know if it's true. So it's false. Which is that any number with digit sum 1 billion, huge number, has at most 5 divisors. Right? At first I was like, well, just make it big enough and you'll be fine. But that's not clear, because if I just chose like a prime number, maybe there's a prime number in the world whose sum of the digits is a billion. It actually might even be possible. So that killed it. And I was like, oh no, I don't know how to even prove it for a billion. Then I was like, I wonder if I can do something with a 9, okay? Because I know at least if my number n is a multiple of 9, you know, like maybe I use n as like 900 or something, I don't know. Then for sure, then my number m would also have to be a multiple of 9, because that's one of these divisibility rules. And then at that point, the divisors of my number m, which is like this number which is with digit sum being this multiple of 9, it's automatically going to have all of these other factors inside it. M is going to have divisors which are 1, 3, 9, and m. And now my hope is like, if I could just force that m is big enough, then there's even more divisors. For example, it would be great if I can also force an m over 3 and an m over 9, and then I'll be done. And an m over 9. So here's a list of 6 things. It's 6 things. There's only one problem. They might be different. They might be the same. It's like I've got this nice big list, but there might be some overlapping between these. So what I'm seeing already is if I had some way of at least knowing that m is big enough, where m is like, where 9 and m over 9 are different, then that would be great. For example, if m was 243, I'd be in good shape. Oh, interesting. But the problem is I don't know that. Because, for example, I can have other kinds of numbers too. Wait. No, it doesn't have to be a power of 3. Now I'm just thinking through this n is a multiple of 9, right? It's like if n is a multiple of 9, so if n is 9, does that work? This is a really hard problem. Either that or I'm just thinking about it the wrong way. So let's see. If n equals 9, could I actually have a number? Oh yeah, of course. Just use 9. Just use 9. And if you just use 9, then unfortunately that has only like 3 divisors. Has only 3 divisors. Yikes. Then in that case, let's go to like bigger multiples of 9. If n is equal to 18. Now, is there a way that I can make... Oh, but I can make this thing have only a few divisors too, right? Or not? Let's see. How do I make 18? What could I do? What if I had a number like 99? If I had 99, then the factors... Oh, that's cool. Ooh, let's count the number of factors. Okay, now I'm thinking, okay? So, how do you find out how many factors there are? Well, 99 is equal to 3 squared times 11 to the first. Now that's kind of interesting. If I have 3 squared times 11 to the first, the number of factors that this has, we've seen it in other live streams, the number of factors will be, you take each exponent plus 1 and multiply them together. That's because every factor is going to be like 3 to the something times 11 to the something. And the first something will be 0, 1, or 2. The second something will be 0 or 1. So this is kind of interesting. I already see that this thing has 3 times 2, which is bigger than 5. That's good, divisors. So this is actually quite interesting. What I'm already seeing is that, gee, if I can just force that my number m is going to be 3 squared times something, right? M is a multiple of 9. Ooh. So this is telling me that m is equal to 3 squared. Oh, that's not supposed to be an equal sign. Implies m is equal to 3 squared times something. Okay. So in particular, if n equals 18, the only time that I would be in bad shape is if this something that I can have here gives me like a power of 3. So do you see what I'm thinking? What I'm thinking is like, if this is 3 squared times any other prime, if that something has any other prime factor than 3 in it, then automatically I will have at least 6 divisors. Okay? So what I just found out is, so if the something has any prime not 3, then m has at least 6 divisors. Did that make sense? It's because then m would be 3 squared times something. And if it was 3 squared times a prime to the first, already you get more than 6 divisors. And if it's like 3 squared times 3 times 23 to the fourth, well, then you get even more. All right? So now what I'm finding out is the only case I need to worry about is what if that something thing is just purely made out of 3s. Well, the only place that I would get at most 5 divisors is if the something was like 1, 3, or 9. That's the only way that I can have up to 5 divisors. Because if I have 9, that's 3 to the fourth total. Okay? So I only need to worry about if this is 1, 3, or 9. Anything else is going to already have at least 6 divisors. So now, if it's 1, 3, or 9, that's going to give me all the powers of 3 from 3 squared, 3 cubed, and 3 to the fourth. Ooh, all of those have digital sum equal to 9. So what that's telling me is I've just proven that if n equals 18, automatically the sum of the digits is, if the sum of the digits is 18, automatically the number has at least 6 divisors. So I know one possibility for n. I don't know that that's the answer because the question asks what's the smallest possible n. But now I know that this is a candidate. Wow, this is a hard problem. How do you do this in a sprint round? Anyway, so this is a candidate because what I've just shown is that if I have 18, the sum of digits is 18, then it's going to be a multiple of 9 thing. Okay, so that's kind of cool. Now the next thing that one would think about is, oh, what about these multiples of 3? Would that be enough? It's like if the sum of the digits is a multiple of 3, well then the number is a multiple of 3. But that's not going to be as exciting. It's not going to give me as much of this. Although we might have something like that. What I'll say is that if I was short on time, I would just guess 18 at this point. Because I'd be like, well, 18 works. There might be something smaller. But good gracious, how would you find them? Because the things that are smaller, I'd be like, I wonder if prime numbers would work for all the rest, except for these multiples of 3. Wow. Because like the numbers from, oh, interesting. So let's start to like pick this apart, right? Maybe we can actually rule out all of the other ones. That would be cool. So let's just try. Okay, so I'm just going to attempt to get rid of all of the other ones, apart from like this 18, right? And some people are commenting it's been 13 minutes, but that's because we just want to understand some math, right? So I'm not actually using these problems just to try to get through the time limit. I'm using these to learn something about math. And what we just got here is a proof, a real proof that if I have a sum of digits being 18, then magically that number has at least 6 factors. That's super cool. So now let's just get rid of all the other cases. What if I have sum of digits equals, well, if it's 1, oh, let's make a table. Sum of digits, if it's 1, and what I'll write here is a number with less than or equal to 5 divisors. And that sum. Okay, so if the sum of digits is 1, okay, let's use 1. If the sum of digits is 2, let's use 2. Actually, any prime number I can just write down. If it's 4, does 4 work? Yeah, 4 only has 3 divisors, 1, 2, and 4. 5, that's a prime number, that's going to work. 6, the number of divisors of 6 is 4, because 6 is 2 to the first times 3 to the first. That's actually how you can see it. Whenever you write the prime factorization, the number of factors is just add 1 to each exponent and multiply. Okay, 7, just use 7. 8, oh, that's good. 8 works, that's just 2 cubed. It's very easy to make the digit sum be like these 1-digit numbers. And 9, we already saw an example, just 9, that's 3 squared, that only has 3 factors. 3 divisors, sorry, 3 divisors. Now let's keep going. Okay, so next one, 10. What if I want the sum of digits to be 10? Well, I can find one for you. How about 55? That's 5 to the 1 times 11 to the 1. And what that tells me is that that's going to have 4 divisors. 1 plus 1 times 1 plus 1. Okay, let's keep going. Let's do the same thing again. I won't write the 2 labels. I'll just write the 2 columns. Sum. Okay? And so 11. How can I make 11? Anyone got some good numbers you want to use? Ooh, a prime number. 47. Right? This is my second column. That's like that thing. 47 is a prime, and the sum of the digits is 11. So that prime number, it only has 2 divisors. 12. Can I make a prime number which happens to have digital sum 12? Ooh, that's hard. You can't make it prime because it's a multiple of 3. But what if I did 57? 57 is 3 times 19. Aha. So if I have 3 times 19, that has only 4 divisors because it's got like, these are 2 primes and each of them, 3 and 19. Each of these are prime, and so the number of divisors is 4. 13, I wonder if I can make a prime number. 49, 85. Can we make a prime number whose digit sum is 13? That would be the fastest. Okay? 9 and 4, that gives you a 49. 8 and 5, that's no good. 7 and 6. Ooh, 67! That's a prime! Bang! It's gone. 14. Can I make let's just use 77. That's easy for me because that's 7 to the 1 times 11 to the 1. And therefore that has 4 divisors. 15. Ooh, that's a multiple of 3. But I wonder if I can do something with like 87. What is that? That's 3 to the 1 times 29 to the 1. Aha! That only has 4 divisors. We're making progress. How about 16? How do you make 16? 9 and 7? Oh yeah. 97, that's like a prime. Okay, that's gone. 97's a prime. We're making progress. 17. How about 17? 9 and 8. 89, that's like a prime. 89's a prime. And that means the answer is 18. Okay, so I suggest that the answer is 18 because so far what I've just found is I found a list of counterexamples. All of these things are numbers which have less than or equal to 4 divisors. 79 would also have been okay. I just have to have 1 prime. Notice how I'm thinking. I'm like, if I have a prime, bang, it's only got 2 divisors. And there could be 3 digits, Skylar, you're right. But that's not a big deal because I just had to list one example of how there's a number with that sum and it has less than or equal to 5 divisors. So I think the answer is 18 because I have a proof that with a digit sum of 18 you have to have at least 6. And I have all these examples up to 17. The moment of truth. It's 18! It's 18! We did it! Okay, all right, and we did it. And we took 18 minutes to solve this. I guess that means that this is very hard to do on the sprint round in a 40-minute time limit. But at least we learned some math, right? Like this is actually, we did a legit proof. And that was actually completely legit. I had no idea what the answer was. But we actually had a proof that at 18, as its sum of the digits, you can't have less than or equal to 5 divisors. Let's do the next problem. Question number 20. 2 circles are externally tangent and have radii r and s, where r is bigger than s. The difference in the squares of their areas is 4010 pi 2. What's pi 2? That's interesting. So I'm not sure what the 2 is doing there. I'm wondering if that's like some kind of like units, because I don't think it's pi squared. But we will find out soon. Yeah. That's okay. Yeah, yeah, it's pi squared. It's squared. Because these are squares of their areas. Totally good. Totally good. So these are squares. Because I was like, since when did the area formula for some kind of circles have pi squared? Well, it's because it's the square of the area. And the distance between their centers is 20. And I've got the sum of the areas. All right, let's go and draw something. So I've got some big circle, R. Big circle with radius R. And a smaller circle with radius S. Let's pretend those are, that's not lined up enough. Drawing one circle is okay. Drawing two circles becomes much harder. But now I'm going to draw this line between their centers. Pretend that that's between their centers. We can make it look more pretend, like this. Okay? And now I have the radii, that's R and that's S. Okay? Now they have this thing about the difference in the squares of their areas. Oh, okay, that's pi R squared minus pi S squared. That's the difference in squares of areas, right? So it's pi R squared minus S squared. Wait. No. What am I talking about? Difference in the squares of their areas. So it's like, it's pi squared R to the fourth minus pi squared S to the fourth, right? Because it's pi R squared squared minus pi S squared squared. And that happens to be 4010 pi squared. And I also know the distance between their centers is 20. So I know that R plus S is equal to 20. And I'm supposed to find out something about the sum of their areas. I want to know what is pi R squared plus pi S squared. And of course, we'll do something with this A and B thing. That's just basically saying it'll be something pi, okay? All right, well, if I see this, the first thing I do is get rid of the pi squareds. I don't like pi squareds. I have R to the fourth minus S to the fourth is 4010. So I know that 4010 is equal to R to the fourth minus S to the fourth. My gut feeling, my gut instinct right away is to do something where I factorize. That's a difference of squares. That's R squared squared minus S squared squared. So that's R squared plus S squared times R squared minus S squared. Okay. Well, R squared minus S squared, I know something about. Oh, interesting. So R squared minus S squared is equal to, so I have an R squared plus S squared times an R plus S times an R minus S. Well, that was convenient. I know that R plus S is equal to 20. So let's divide that out, right? This is 20 here. That's no fun. If I divide this out, 4010 is not divisible by 20. I don't like fractions. But it doesn't look like I have much choice. All right. So now I'm looking at this in a different way. I'm like, I wonder if there's anything else I can do. I guess I could do it with fractions. Oh. Interesting. So let's go to the next screen where I have some space. I'm going to at least write down, I'll divide it through. Okay, I'll divide it out. Let's divide out the 20. Right, this thing is 20. So if I divide out the 20, the 0 goes away, and I get 401 divided by 2. I'll write it. Do I want a decimal? Maybe I'll just call it 401 over 2. Let's do that for now. I don't yet know if I want to do decimals or fractions. 401 over 2 is equal to R squared plus S squared times R minus S. Yuck. Now what? So I have to somehow use this together with the R plus S equals 20. Looking at this some more, I see that it might be time to play the guess and check game. The reason I'm saying that is because it says the sum of the areas is AB pi. That means that if I add the areas together, it's an integer multiple of pi. And if the area sum is an integer multiple of pi, what that's telling me is that this R squared plus S squared is an integer. If R squared plus S squared is an integer, and R plus S is an integer, I feel pretty good at saying there's a decent chance that this just happens to have integer solutions. It's not a guarantee. Sorry, I'm like r squared plus s squared is an integer, r plus s is an integer, and r to the fourth minus s to the fourth is an integer. So I'm like, it seems like we have enough integers around to give me some hope that maybe the answer happens to be with integers. And I'm very quick at checking those because there aren't that many ways to have integers which add up to 20. So we can very quickly just check those. If none of those work, then we go back to the drawing board, okay? So I'm going to go back to here. It's like r to the fourth minus s to the fourth. That was supposed to be, wait a second. I think I just got a proof they're not integers. Because if I look at this, I'm like, if I have this, then r to the fourth plus minus s to the fourth is 4010. Okay, which I factorized this way. And then I just like factorized more. And then I divided out this r plus s, which was 20. Okay, and so now I got this thing. And so there's no way in the world that r and s are integers, because if I was trying to add this stuff together, right? If I was trying to add this stuff together, there's no way I'm going to be able to get this. Okay, now what else can I do? Do I have any hope that they're at least rational numbers? Because right now I have two equations and two unknowns, really. I have this r plus s is 20, and I've got this nonsense. Ooh, I have some crazy idea. Okay, now this is just like a crazy unfair idea. I'll be like, I wonder if I can express, so this is r plus s, and like I can use r minus s as my other variable. Let's actually legit solve for r minus s. You know how I'm going to do that? It's because I can take the r squared plus s squared, and I can turn that into something that is involving both r plus s and r minus s, like this. Okay, I have this mysterious r squared plus s squared. Yuck, I don't know what that is. But I know something about r plus s whole thing squared. If I decided to square this, well, that's r squared plus 2rs plus s squared. And you know what happens if you take r minus s whole thing squared? That's r squared minus 2rs plus s squared. Aha. Now, in that case, you know how I can use these two to get that? What I'm saying is I know what r plus s is, right? R plus s, I know what that is. That's 20. I'm saying that, you know, I'm going to try to get r minus s. My instinct is, look at this. I have an r minus s here. What if I call that an unknown? Let's call it x, because I don't know what it is. If only I could write something here in terms of x, that would be awesome, right? But I can write something here in terms of x. Yes, I already see somebody from the comments has pointed out, if you just add these things up and divide by 2, it's that. So r squared plus s squared. So r squared plus s squared is just equal to r plus s whole thing squared plus r minus s whole thing squared divided by 2. So that's just going to be 20 plus this x, right? X is what I didn't know what it was. R minus x. R minus s was x. 20. What happened? I have to square things. Bye-bye. Bye-bye. It's 400 plus x squared divided by 2. Is this okay? Because I have r plus s whole thing squared. So now that I have this, let's go and put everything together. I have 401 over 2 is equal to, I have the r squared plus s squared, which is 400 plus x squared over 2 times x. Hey! I think we just found something. Look at that. How in the world can I make these be equal? Oh my gosh! I can make x equal to 1. This is, by the way, I was scared because this is a cubic equation. It has x cubed in it. I don't know the cubic formula, so I would fall down to like a guess and check or something at this point. But it's like, oh wow, if I do 1, like that makes 401 over 2 times 1. Okay, that's it. X equals 1. What was x again? X was r minus s, right? Yeah, x was r minus s. That's how these halves came in. Okay, so I just found out that r plus s is 20 and r minus s is 1. So that means that R is like 10.5 and S is 9.5. Okay? So it's like 20, what is it? Let's go. What did I have? So I have R plus S is 20. I want to be careful not to use too much space. So what I just found out here is, let's go over here. R plus S is equal to 20, and R minus S is equal to 1. That means that it's like R and S are like 10 and 10, but off by half in each way. So R is equal to 10.5, which is 21 over 2, and S is equal to 9.5, which is equal to 19 over 2. Hooray! Now let's go and figure out what we were supposed to figure out. It says the sum of the areas. Okay, I guess we sum the areas, right? What? Is this going to work? Now I'm not happy. Like, what if I get fractions? We'll find out soon. This looks like I'm going to get fractions. Uh-oh. Did we make a mistake? I need to have pi times r squared plus s squared. So if I actually did some squaring, because I'm like, anything 0.5 squared is 0.25. So that means that if I add them together, I'm going to get a 0.5. I don't like this. There's a mistake somewhere. Because it looks like a and b are supposed to be whole numbers. Oh, wait! Is there a typo? Is this a over b times pi? Because otherwise, why in the world would it ask me for GCD AB equals 1? I bet there's a typo in the way that we transcribe the problem. So I'm going to answer the question, and this is not Math League's fault. I'm going to answer the question where I think that what was meant to be written is this. That's my guess. Okay? I'm guessing it's this because nobody in their right mind would ask you to give like an answer of like just randomly factorize out the a and b. Okay, so let's just put this in. And this is not you guys' fault, Math League. This must be us transcribing it. Must be a over b. Okay, now I'm happy again because I'm back in the land where fractions are okay. And let's now put it together. And actually, we are very honored today to have Tim Sanders here. Tim Sanders is the person who runs Math League. So this is pretty cool. So let's keep going. So let's do this. I have this. Let's just square it, right? I just need to know the sum of their areas. Okay, so it's going to be pi. Let's write it down. Sum of the areas. Sum of the areas is equal to pi times 21 squared over 2. That's 441. Sorry, 21 over 2, whole thing squared. That's 441 over 4. Plus 19 squared, I think it's 361. It's been ages since I did this stuff, but I can check it in my head. The way I'm checking it is because I know that 20 squared is equal to 400. And there's this thing about the difference between two consecutive squares, like 19 squared and 20 squared. The difference between them is 19 plus 20. And that's like the difference between 361 and 400. Similarly, the distance between 20 squared and 21 squared is 20 plus 21, which is why I have a 41. Now let's finish. So that's going to be equal to pi times, what is this? This is hard. Arithmetic is very hard. 1 plus 1 is 2. 4 plus 6 is 10. 802 over 4. Do I believe that? Yeah, I actually do believe that. That should be like 400 plus 400. Okay, this is good. Okay, thank you very much, Tim, for explaining that we copy-pasted wrong from your test. It was a good test, but that was our fault. Let's continue. So I have this 802 over 4. Let's simplify that, okay? So, yeah, I bet that's what happened. I bet we did a copy-paste, and that's what happened. But let's keep going. So let's simplify. Pi times 401 over 2. By the way, the 802 I like, because remember I said that the difference between 400 and this guy is you minus 20 and you minus 19. And to go up to this guy, you plus 20 and plus 21. And since 21 and 19 are 2 apart, that's why this should be 2 away from 400 times 2. So now I'm here, and the question asked me to add together the 401 and the 2. So I'm going to say that the answer is 403. Let's see if this works. It works! Okay. Yeah, the 401 is back. By the way, these are really, really nifty questions. I expected that I'd get caught on that one, because I was like, I don't know how to solve a cubic equation. All right, we got some more time. Let's keep going. Question 21. Drink of water. In each unit square of a 3 by 3 grid, exactly one of the digits, 1, 2, or 4, is written. How many ways are there for the grid to be filled so that each vertical number read from top to bottom and each horizontal number read from left to right are divisible by 4? Oh, neat. Okay, so we're going to write down some numbers 1, 2, and 4. Question looks scary. That is a very concave square. Let me try to draw a non-concave square. Okay? I just want to visualize what in the world is going on. So I've got stuff like this, and I'm going to be writing some numbers down. And I need to have that these numbers and those numbers are all divisible by 4. Well, that tells me don't put any 1s out there. All right, so these aren't 1s. That's clear. Oh, neat. So there's some like nifty fact about a number is divisible by 4 exactly when the last 2 digits are divisible by 4. And the reason for that, by the way, is because the number is like, 700 something something. Oh yeah, you know that 100 is divisible by 4. So if you have 700 something something, the 700 is not going to change whether you're divisible by 4 or not, because you're adding a multiple of 4 in the 700. So that's why the last 2 digits are what matters. So now what do? Now I need to be like, I need that each of these 3 pairs is a number which is divisible by 4. Now I need to know, how do I make numbers divisible by 4 with 1s, 2s, and 4s? Well, I can think about how they end. If they happen to... Maybe that's a weird way. What if how they start? Well, I like how they end. I'm having this crisis of deciding whether I want to use how they start or how they end. Let's use how they end since that's what I said. So how they end, it could be 1, 2. That's a multiple of 4 if it ends in a 2. But if it ends in a 2, it's only going to be the 1, 2. Because if it ends in a 2, to be a multiple of 4, that guy's got to be odd. Now, either the other way is that it ends in a 4. And at that point, I can do 2, 4 or 4, 4. If I want a number to be a multiple of 4, these are the only options for the last 2 digits if I'm using the digits 1, 2, and 4. Okay. Well, once I look at that, then I say, there's a bunch of choices. So if I put a 1 here, for example, I would be able to go with 2. I'm trying to think of how I want to break this apart. Because you see, to me, these 3 numbers are really important. Maybe that's how I should think. So these 3 numbers are 1, 2, or 4. Okay, so I've got these 3 numbers here. These are really important. They force a lot of things. I'll just do like a random example. Like suppose I put a 1, a 2, and a 2. Just randomly drop those there, okay? If I did that. Now, that's going to force me to have a few things. Because you see, now I'm seeing like the first digit is quite interesting of the 2 digits. If I had this, I have forced myself to put a 4 here because this has to be a 2, 4. I have forced myself to put a 4 here. And I forced myself to put a 4 here. Okay? What else have I forced? I have the 1 here, and that has forced myself to put... Wait a second. It's always forced. Wait, I'm looking, it's like if it's a 1, it's forced. If it's 2, it's forced. If it's a 4, it's forced. So the 1 is also forced. The 1 has to have a 2. And then the deep question is like, what happens here? Oh, neat. So in this case, the 4 forces me to finish with a 4, and that's okay. And what I'm also seeing is no matter what I got forced here, there will be exactly one way to force down there. Force because this number and that number both have to be legit. That means that these 2 digits and those 2 digits have to be legit. Fortunately, from the 2, they force the same thing because the 2 forces a 4, and then the 4 is going to force a 4. So what I'm seeing here is kind of nifty. I'm seeing that whatever I write down in these 3 positions, they are going to force what happens next. Do you see that? Like, this is how I solve a problem, by the way. I monkey around. I just kind of say, I don't know, let's stuff those numbers there and see what happens. And I say, oh, neat. I got forced. And by the way, I can do whatever the heck I want up there. I can just do anything there. Because that's not going to change whether my number is divisible by 4 or not. So that's fun. That can be anything, star for anything. By the way, I'm already coming out to, I think the answer is 27. 3 times 3 times 3. But to make myself more sure of this, I'm just going to play another game and just be like, well, let's try it again. Let's write some more random numbers. I don't know, what's your favorite number? 4, 4, and 4. What happens there? If I did 4, 4, and 4, watch how it forces. So that 4 forces a 4. Actually, everything is forced. These are all 4s. It's called 4, 4, 4, 4, 4, 4, 4, 4, 4. All 4s. Okay? I didn't expect that to happen. But let's do something else, which is not like all 4s, just to prove the point, right? Not really prove the point. I think we already proved the point. But like random other stuff. 1, 4, and 2, like that. If we did that, the 4 here forces a 4. The 1 here forces a 2. These are really neat questions. This also forces a 2. That 2 forces a 4. And both of those 2s force the same 4. What I have seen is that I really can do whatever I want here. Wait, no, the answer is not 27. What in the world am I talking about? It's not 27. No. So it's 81. It's 81. Because I have 4 places that I can play around, right? So the point is like, when I think of the purple stuff, I can do anything I want in each of those 3 purple spots, and that will force the rest. And I can also do anything I want in the top spot. So I have 3 choices, 3 choices, 3 choices, 3 choices. My guess is that the answer is 81. Because I can do anything that I want in any of those spots. Let's see. Is it? It is. Okay, we're good. We got some more time. Let's do some more problems. It's 2020. No, it's not. It's 2021. But that's okay, because 2020 is an interesting number. State sprint number 23. What is the remainder when, good gracious, what? 7 times 49 times 343 times 2401 is divided by 2020. Well, first of all, I see some mysterious 7s, okay? Like, that's a 7, that's 7 squared, that's 7 cubed, so I'm guessing that's 7 to the 4th. Is it? It is. You know how I know it is? It's because 7 squared is 49. 49 squared differs from 50 squared by 49 plus 50. That does. Because 50 squared is 2500. 49 plus 50 is 99. So I have powers of, this is a power of 7. So, okay, what's this? This is 7 to the 1, 7 to the 2, 7 to the 3, 7 to the 4. That's 7 to the 1 plus 2 plus 3 plus 4, which is 10. All right. So, I mean, can't be that bad. We could just do it. Is that what Math League meant for us to do? Just do it? Watch this. We're going to do something crazy. Okay, 7 to the 10th. I'm lazy. Everyone who has watched this live stream knows that. I don't actually want to find 7 to the 10th. But I'm going to divide by 2020. And Math League already very conveniently told me 2401 looks kind of like 2020. So what I'll do is I'll write 7 to the 10th as 7 to the 4th times 7 to the 4th times 7 squared. Why? Because that's just equal to 2401 times 2401 times 49. Now you know what happens. If I'm going to divide by 2020, I can replace each number by already reducing it modulo 2020. Because 2401 happens to be 2020 plus what? 381? Is that right? Yeah, arithmetic is hard. So this is 2020 plus 381 times 49. Okay. Now, if all you care about is the remainder, I can throw away the 2020s. Because if you went and FOILed the whole thing out and expanded, if you expand the whole thing out, then you won't have to worry about the 2020s because there'll be 2020 times other stuff. And after what happened last year, I think we want to forget about 2020 anyway. So then let's just say the way that we usually write this is we usually write 3 horizontal lines, and we write 381 times 381 times 49 mod 2020. Okay, I guess I have to write it down. But so what I have here is this just means that if I divide it out by 2020, this will have the same remainder as that. So now I only have to do this amount of work. I'm still pretty lazy. That's no fun. Do I really have to multiply all that? Let's see. Drink some water, hope for inspiration. I guess I could make the numbers a little bit nicer. Is that right? 49 is close to 50. 50 is a factor of 2020, but that's not going to help me too much. Okay. I guess we can just bite the bullet and do it. I guess. Okay. Again, some of you may have clever ways. I'm actually not looking at the comments right now because I want to see if I can actually get this. Yeah, I guess my attempt at being clever has ended. So, okay. So I'm not very good at multiplying three-digit numbers by three-digit numbers. So I guess I could, but do they really want me to do that? There must be some other way to do this. Because I thought I was so clever when I went and used the 2401 and reduced it by the 2020. You can see I'm just thinking. I'm like, I wonder if I should have just reduced it once. No, that's no fun. Okay. Okay. I guess we can bite the bullet and do it. You can see that the way I am is I'm just like doing this kind of multiplication scares me because I'll probably do it wrong. But let's just go. Okay, so let's try. So 381 times 49. Let's go. 9 times 1 is 9. And you can see how I am. I'm like, if there's any way I can avoid doing this, I would rather try to think first. But I really don't see something right now that can help me. Okay, 9 times 1 is 9. 9, 8, 72. 9 times 3 is 27. Yeah, okay, 27. 34. Okay, 4 times 1 is 4. 4 times 8 is 32. 4 times 3 is 12, so that's a 15. Okay, 9, 2 and 4 is 6, a 6, 8, and a 1. By the way, the reason I did that one first is because I was like, that'll be a number in the like 10,000s-ish, which is nice to mod by 2020. Because I can just go and say, you know, I can do 2020 times 9. That's 18,18,0. That's not really how you say a number, but 2020 times 9 is going to get 18,18,0. But now I can subtract this very nicely. You know, if I took 18,669 and I subtract out this like nearby multiple of 2020, I get a number that's not that bad. So if I subtract out the 18,18,0, which I've just invented as a new way to call a number, that would be 9. 16 minus 8 is 8. That becomes a 5. 5 minus 1 is 4. Okay, so now I have some painful thing of I have to do 489 times 381. Oh no. Okay, so now what happens? So this is going to be the same as 381 times 489 modulo 2020. Now there's a big multiplication. Oh no. That's 3 digits multiplied by 3 digits. Am I even going to be able to do it without making a mistake? Let's see. By the way, I'm looking at these numbers and I'm like, I wonder if there's something nice about them. They're both around like 400-ish. Can I use that? Not well. Yuck. Yuck meaning like I'm probably not finding the best way. I saw that somebody's commenting Chinese remainder theorem. That might work, but that also scares me a bit because 2020 has a lot of factors. All right, let's bite the bullet. Let's do it. 381 times 489. Here we go. 489, 381. Go! 9, 8, 4, 8, 9, 72. I think. Yeah, 8 times 8 is 64. 71. Yeah. Notice how I multiply. I like do something and I check it as I go. 8 times 4 is 32. 32 plus 7 is 39. Yeah, okay. Good. 3 times 9 is 27. 3 times 8 is 24 plus a 2 is 26. 3 times 4 is 12. 12 plus 2 is 14. All right. 9. 8 and 2 is 10. And now I have 1, 4, 1, and 7. So that's like 6. 4 plus 2 is 6. 6, 7 is 13. Okay, 1 and 9 is 10. That gives me a 16. 3 and 4 is 7. That's an 8. 1. All right, let's go. Now we just have to go and divide this thing by 2020. Okay, just do it. 1, 8, 18,6,309 divide by 2020. Okay, I have to go out to the 18,18,0. Hey, I had that already. So 9 gives me an 18,18,0. Subtract. Wait, is this the same number? 1863? No, it's a different number. 186 was around. Anyway, subtract, I get an O. 13 minus 8 is 5. 5 minus 1 is 4. 4509. Okay, times a 2. 4040. Subtract, and I get 9, 6, 4. 469. All right. Is that right? I'm just checking to see if I made a mistake on my arithmetic, which is quite likely. Let's try it. 469. Let's see if this is correct. 469. It is. How do you do this? So I mean, we did it, but I wonder if there's a better way. Wait, that wasn't hard? I mean, it was hard for me because if you noticed, I struggle a lot whenever there's arithmetic because it's so easy to make one mistake and then it's an oopsie doopsie, right? We cannot afford to make even one mistake. Okay, now, anyone in the comments want to tell me a better way to do this? there must have been a better way than my like bang, 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 bang. But if somebody in the comments saw that there was something else, we can learn from you. But I'll just share like my angle was just make the numbers smaller. Possible for okay. So Tim Sanders, the organizer of the contest, says the Chinese remainder theorem was the way to go. So so these are all powers of 7 modulo each of those numbers 2020. I see we could do that because I could use, this is a power of 7, right? I could figure out what is 7 to the 10th modulo when I divide it by each of the factors of 2020. But I'm still scared of like how to put them together at the end. Because it's like, even if I found out what they were at the end, I'd have to put them together somehow. So again, I'm sure that you guys have some really clever way, but I think I'll pass on this because I don't see it as fast as all of you. Let's keep going. Let's do one more question, and then maybe we can take some random Q&A at the end. Oh no, question 27. Where are we going now? For each positive integer n at least 3, let f of n be the number of interior diagonals of a regular n-gon. Jonathan adds all the values of f of n, starting from f of 3 and ending with f of 2021. What is the remainder when Jonathan's result is divided by 2021? Okay, so I need to just like add up some numbers, but there's a long list of them. So first of all, how many interior diagonals are there anyway? So the way you can do this is if I have a regular n-gon, then there are n vertices, and each vertex has n minus 3 other things you can go to, but you have to divide by 2 because you double count each diagonal. What I just did here is I said, look, this is an n-gon, trust me. And if I have a 1 vertex, then the interior diagonals have to go to everything except those 2. Right? The interior diagonals go to everything else. So that's the n minus 3, and I divide by 2. Okay? So now I need to kind of add this up. I need to go and add up all of these numbers from f of 3 up to f of 2021. Is there a good way for a lazy person like me to be able to pull this off? Well, there is something I know, which I don't know if is the idea of what you guys are expecting to do here. But there are some formulas for adding up all of these like arithmetic sequences. And sorry, if I write a sequence, not arithmetic sequences, but like if I have a bunch of squares. But this thing with an over 2 makes me think of a choose. Oh yeah, actually I know what it is. This is also equal to n choose 2 minus n, right? That's definitely the case. N choose 2 minus n, because n choose 2 is the number of ways I can find 2 of those vertices and connect them, and the minus n is you subtract the outside. And you can also see that would be the case because n choose 2 is n times n minus 1 over 2. And if you subtract an n, that's exactly how you get an n minus 3 over there. Okay? All right. Now, here's the interesting thing you can do. If I want to know the sum from f of 3 all the way up, there's a crazy trick you can do once you have these. I need to know what is 3 choose 2 minus 3 plus 4 choose 2 minus 4 plus, oh wait, I want to write it in a different way, okay? I'm going to write it in 2 rows. I'm going to write that the the question, I have to divide something by 2021. But I'm going to have 3 choose 2, minus 3. Next one is 4 choose 2, minus 4, but I put a minus in the bracket out there, so it's plus. 5 choose 2, minus 5. I write a plus because there's a minus outside. Goes on forever. No, it doesn't. It goes on until 2021. Choose 2 plus 2021. Okay, now I did this on purpose. It turns out that if you add up all of these things, it is super cool. What happens if I add up a lot of choose 2's? Well, it turns out that this is like a diagonal on Pascal's triangle. So you may have seen before sometime this Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay? Where are the choose 2's? The choose 2's are actually all here. Right? In fact, the 3 choose 2 is that one. The 4 choose 2 is that one. The 5 choose 2 is that one. And that's a 2 choose 2. But do you know what happens if you just, for fun, add these together? 1 plus 3 plus 6 plus 10. You know what that is? Well, 1 plus 3 plus 6 is 10, plus another 10 is 20. Oh, look at that. That's the number that goes right there. Wait a second. What happens if you add 1 plus 3? It's 4. What if you add 1 plus 3 plus 6? That's 10. Do you see this? This is actually called the hockey stick identity, because it looks like a hockey stick. If you go from here, it's the next one. You know why that's true? The reason that's true is because, watch, if I already know that that sum is equal to 20, what would I get if I tried to also add the next number on? If I wanted to add the next number on, that's not 20, 15. If I wanted to add the next number on, well then the sum of all of these is the same as the sum of those 4 and that 15, which is the same as the sum of the 20 and the 15. Oh, look at that. The way you make Pascal's triangle is the thing right under it. So I've just showed a proof by induction, actually, that if I add up all of these, I always get the thing that's down there. And specifically, what is this? This is like 2 choose 2 up to 4 choose 2 adds up to 5 choose 3. That's what we just had here. 2 choose 2 plus 3 choose 2 plus all the way to 4 choose 2. That's equal to 5 choose 3. Because it's like the next row down and one across. So now you can see that something really nifty is happening. Hey, look at this. What's the top row? The top row is just equal to 2022 choose 3. Just kidding, minus 1. What's the 1? 2 choose 2. Because we didn't have the 2 choose 2. If I had a 2 choose 2 and went all the way to here, I would get 2022 choose 3. You know why I'm happy? I wonder if that, I wonder if that's a multiple of 2021. That would be super cool. Okay, we'll figure it out soon. But now I have to do this thing too. Minus this. What's this? Well, it's like the sum of an arithmetic series. Actually, the way I'll write that is if it was 1 up to 2021, that's going to be 2021 times 2022. Let's write that way. 2021 times 2022 over 2. And then minus the fact that I'm missing the 1 and I'm missing the 2. Did that make sense to people? I'm like, the sum of the numbers, 1 plus 2 plus 3 up to 2021, that's 2021 times the next number over 2. All right, now my hope is, ooh, look at that. That's a multiple of 2021 because when I cancel, the 2 only goes out of that part. And I only care about the answer when I divide out by 2021. So that's not going to matter. It's 2021 times something, 1011. I don't care. How about this thing? What's 2022 choose 3? What does that have to do with 2021s? (2022) times 2021 times 2020 all over 3. Oh, look, no, 3 times 2. Look at that. I love it. This 3 times 2. The 3 cancels out of that one because the sum of the digits 2, 2, and 2 is 6. So that's going to cancel out that way. Stuff. I don't know what it is. Some stuff. And the 2 cancels the other way. I know what that is. 1010. Bam! It's a multiple of 2021. So that means that now I can just apply some mod arithmetic. So if I look at the answer, what do I get? I get multiple of 2021 minus 2 choose 2, which is 1, 1, and 2. So minus 4. Hey, that means the result is minus 4. No, that's not a legit remainder. But what do I do to make minus 4 into a legit remainder? Just take 2021 minus 4, and that would be the answer. I don't need to write that carefully. I know what that is. 2017. A year when the world was normal. Okay, let's see if the answer is 2017. Just reading the problem, making sure I think I read everything right. Okay. Wait. No. There's a subtraction. There's a sign error. This is why I'm checking my work. I'm like, just a second. This is a minus sign. Oh boy. Now, this is why checking is important. Take back what this is. No. So actually, it's not going to be that, because I have to minus it, so that becomes pluses. Boop. Wait, now it's easy, because now it's just like minus 1 plus 1 cancels. It's just 2. Pause again, look at the question again, make sure we didn't make a mistake. So it's like, what was I doing? I was adding from F3 up to F2021. All right, so we had all of these, and we had the subtraction. We subtracted some multiples of 2021. That's good. And this had some minuses, but the minuses are inside the minus, so it becomes plus. I think we're good. All right, let's see if the answer is 2. It is! And with that, we have actually finished the live stream. Thank you very much to Math League for writing these really interesting questions. Thank you very much to Tim Sanders for coming and attending this session. And thank you to all of you for coming on and playing with some pretty hard questions. I think we got to learn some neat things today. I certainly did. And, well, I look forward to our next collaboration with mathleague.org. Until then, have a great evening or a great morning, or wherever you are in this world. See you next time.